Hello friends, myself Ashok Bagda from Dr. Subhash Technical Campus, and in today's lecture we are going to discuss about critical speed of shaft carrying a multiple rotor from the subject of dynamics of machinery. So let us start. So let us consider a shaft having negligible mass. So the shaft having negligible inertia carrying a rotors, multiple rotors having mass m1, m2, m3 and m4 and so on. So consider a shaft having negligible inertia and carrying multiple rotors. Let m1, m2, m3 and m4 be the mass of each rotor and y1, y2, y3 and y4 to be corresponding deflection as shown in figure. So here y1, y2, y3 and y4 are the deflection of shaft, and because of that this is the deflect position of shaft. This is a position of shaft in static condition and this is a deflect position of shaft. Now we can calculate the natural frequency or a critical speed of shaft by using two methods. First one is a Rayleighs method. So let us see, first one is a Rayleighs method. This method is based on principle that maximum kinetic energy is equal to the maximum potential energy. The maximum kinetic energy is equal to the maximum potential energy. So we know the equation of maximum kinetic energy and maximum potential energy. So maximum kinetic energy, first of all, maximum kinetic energy is the total kinetic energy. So the kinetic energy because of this mass m1, kinetic energy because of mass m2, kinetic energy because of mass m3 and kinetic energy because of mass m4. So kinetic energy but maximum. So we can say that is nothing but is 1/2 mv square. So here it is for mass m1. So we write 1/2 m1 v1 square plus 1/2 m2 v2 square plus 1/2 m3 v3 square plus 1/2 m4 v4 square. If there is a multiple rotor, then we can say that so on. We again rewrite this equation. Now we know that the velocity is nothing but omega into its deflection from its neutral axis. That means omega into r. We generally write natural frequency, we generally write velocity is equal to omega into r. So here we rewrite this equation. Kinetic energy maximum is equal to 1/2 m1. So v1 is equal to, so the all the rotor having same speed, that means all the rotors we consider critical speed of shaft. So in a critical speed, the all the rotors are rotating with omega c critical speed. So 1/2 m1. So omega c is a angular velocity into deflection is y. So y1 into omega c whole bracket square plus 1/2 m2 in bracket y2 into omega c whole bracket square plus 1/2 m3 in bracket y3 into omega c bracket square plus 1/2 m4 y4 into omega c square and so on. So in a general, we rewrite this equation in a general way. Maximum kinetic energy equal to 1/2 omega c square sigma I is equal to 1 to n mi into yi square. So maximum potential energy, the maximum potential energy we know that in a general we can say that maximum potential energy is equal to, if this is a delta and this is force, then we can say that maximum, this is the maximum potential energy is equal to F into delta. So maximum potential energy is equal to 1/2 F delta. So here 1/2 we write, so delta is y1 and F is equal to nothing but is equal to force. So m into g. So 1/2 m1 g into y1 plus 1/2 m2 g into y2 plus 1/2 m3 g into y3 plus 1/2 m4 g into y4. We know that why mg? So because force in this direction is a weight. So weight is m1 into g. Maximum potential energy is equal to 1/2 m1g into y1 plus 1/2 m2g into y2 plus 1/2 m3g into y3 plus 1/2 m4g into y4 and so on. So in a general way we can say that maximum potential energy is 1/2 into g in a sigma I is equal to 1 to n mi into yi. So according to the Rayleighs method, kinetic energy maximum, according to the Rayleighs method, maximum kinetic energy is equal to maximum potential energy. So 1/2 omega c square in a sigma I is equal to 1 to n mi yi square is equal to 1/2 into g sigma I is equal to 1 to n mi into yi. So we get omega c is equal to under root g into sigma I is equal to 1 to n mi yi upon I is equal to sigma I is equal to 1 to n mi into yi square. So fc is a natural frequency is omega c upon 2 pi. So 1 upon 2 pi under root g into sigma I is equal to 1 to n mi yi upon sigma I is equal to 1 to n mi into yi square. So this is a natural frequency of rotor carrying a multiple. Now another method is a Rayleighs method. So the critical speed of shaft carrying a multiple rotor or a number of points load acting along the uniformly distributed load is obtained from Rayleighs empirical equation. So this is based on empirical equation. So in which we can say that 1 upon omega c square is equal to 1 upon omega c1 square plus 1 upon omega c2 square plus 1 upon omega c3 square plus 1 upon omega c4 square plus up to so on. So where omega c is a critical speed of shaft carrying a number of point loads and uniformly distributed load. So now in this case we have considered the rotors. Because of the mass of rotor, some load is acting on the shaft. If we consider this is a rotor and these are the masses. So because of m1 mass, some m1 g1 is force acting here, m2 g2 is force acting here, m3 g3 is force acting here, and m4 g4 is force acting here. So we can consider uniformly distributed load. So omega c1 is a critical speed of shaft neglecting the mass and all the points load except point load. So we only consider only point load. Same way, omega c2 is a critical speed of shaft neglecting its mass and all the points load except points load 2. Similarly, omega c3, omega c4 and omega cs. So omega c is a critical speed of shaft considering its mass and neglecting all the points. So omega cs is a critical speed when we consider only its mass. And let us consider delta 1, delta 2, delta 3. So static deflection of shaft due to weight load W1, W2, W3 when considered separately. And delta S is a static deflection of shaft due to self weight or due to the uniformly distributed load. So we know that natural frequency of transverse vibration or a critical speed due to the load W1 is omega C1 is equal to root G by delta 1. Similarly, omega C2 is root G by delta 2. Similarly, omega C3 is root G by delta 3. And omega C is equal to root G by delta C. So if we put this value in this equation, then we can calculate the critical speed of. Let us see one animation for a shaft carrying multiple rotor.